So, before we actually get into the heart of chapter 21 and talk about confidence intervals, I wanted to think back to the last slide from the first part of this lecture where we talked about having a big enough sample size. And I thought maybe showing some pictures might help illustrate what we mean by this. So, I want you to imagine that we have a simple random sample of 15 M&M candies. And we're taking that sample to try to estimate the proportion of orange candies in the population. So I take a sample of 15, I determine the proportion of orange, and we imagine that we take lots and lots of samples of 15 M&Ms, and we have lots and lots of proportions of orange candies, lots of sample proportions, and we plot those sample proportions in the form, again, of a histogram. So what might that distribution look like? Well, we actually did this, and this is what we got. So I know this is a little bit small here, but I'm hoping that as you're looking at this, you're seeing that it's not perfectly normal. It's kind of getting close to a normal distribution, but there's a little bit of skewness here. And part of the reason for that is that we have a pretty small sample size here. We only have 15. And so if you think about some of those formulas that I showed on the last page, I'm not going to apply them here, but you might think about how you would apply them. So let's say, for example, that you get a sample proportion, or p-hat, of 0.20. So again, we're assuming here that all we know is p-hat. We don't know p. So you'd have to use that second set of formulas. So take 0.20, multiply that by 15. Think about what you get. Is that number greater than or equal to 15? Take 1 minus p-hat, which would be 1 minus 0.2 or 0.8. Multiply that by n. Is that number greater than or equal to 15? So again, I challenge you to do that. You don't have to do that. But I'm hoping when you do that, you'll see that we just really don't have a big enough sample size when we only have 15 M&Ms. And that's why when we look at lots and lots of sample statistics, we're not getting something that's perfectly normal. It's starting to approach normal, but it's clearly not normal. And so if we were to go on to use what we know about the normal distribution to compute a z-score or to apply the empirical rule, we would make some mistakes along the way. We wouldn't come up with numbers that are as accurate as they can be. Contrast this, however, with what would happen if we increase the sample size. What would happen now if all of a sudden we had 50 in our sample rather than 15? So now you can see, so we did this again. We took lots and lots of samples of size 50. Now we can see a lot more symmetry, much more of a normal distribution. And again, if we assumed, for example, that we had a sample statistic of 0.20 and we applied those formulas again, you would see there we meet that threshold. We do have something that's greater than or equal to 15. So we can be much more confident now that our underlying sampling distribution is normal, and we can move on to use what we know about the normal distribution. Okay. So let's jump into it. Confidence intervals. Confidence intervals, this is really the heart of chapter 21. So we're constructing a confidence interval again because we want to estimate an unknown population parameter. So we really want you to know the goal of a confidence interval. You're trying to estimate something unknown about the population. You're trying to estimate an unknown population parameter. And you might remember way back in chapter 3, you learned a little bit about constructing a confidence statement. You learned about estimating the margin of error if you didn't know that, if you weren't given that as part of a news story. We showed you this quick estimate formula for figuring out the margin of error. So we want you to put that out of your mind now. So way back then, we were just introducing you to these ideas. We definitely want you to think about what you learned about what the margin of error is in chapter 3, but in terms of estimating it, we now are going to teach you a very precise method for determining more clearly what the margin of error is. We're no longer going to just estimate it, but we're going to use our sample data to actually compute a more precise margin of error. Okay, so again, we no longer want you to apply that quick estimate. So moving forward, if we ever ask you what's the margin of error, if we ask you this in relation to chapter 21, or if we ask you this perhaps on the final exam, we want you to actually apply what you've been learning in chapter 21. We want you to use those formulas, and we'll practice them in a moment. So the big question, I guess, is why we actually need a confidence interval. So we want you to think about that. And hopefully through reading chapter 21, and also maybe going back to chapter 3, you have a good sense of why we would need to do this. Why can't we just obtain a sample statistic and use that sample statistic to say something about the population parameter? For example, why can't I just take one sample of M&Ms and say, hey, I got 20% orange in this one sample, so in the whole population there must be 20% orange M&Ms. Why can't we do that? And again, I'm hoping that you're thinking about why you can't do that. I'm hoping something is coming to your mind that would prevent you from doing that. I'm hoping that you're thinking about this idea of sampling variability, or the random variability that's involved in taking a sample. I take a sample of a certain size and I get a certain sample proportion. Someone else will come along and they might get the same thing. They might get something a little bit different. We take lots and lots of samples. We get different things. And so we have to take that into account when we're trying to estimate what's going on in the population. If each sample is a little bit different, how exactly do we know what's going on in the population? That's where we have to take our sample statistic. We have to consider the margin of error, which helps us to measure that variability that we'd expect to see from sample to sample. And together we use those two things to help us construct an interval that we hope will include that true population parameter. So before we jump into this, again, one really important thing to keep in mind is that you might be dealing with proportions. So you have to think about, is the data I collected in the form of a proportion, or is it in the form of a mean or an average? And for some of you, it might be really easy to tell the difference. For others, maybe not. You're not really sure. Proportions and means, they're both numbers. So, how do we know which is which? So we hope after the end of this chapter that you'll understand. And again, it's important to understand because the way you construct a confidence interval, it'll be a little bit different depending on whether you have proportions or means. When we go on to the next chapter about significance testing, when you do a hypothesis test, you have to know if you have a mean or a proportion, because that's going to have some bearing on what you do with your sample data, what kinds of numbers you compute to actually carry out the test. So we want you to be comfortable and confident in terms of figuring this out. So in terms of proportions, we, again, if you have a proportion, it means the original question that you were asking was categorical in nature, or would lead to a categorical response. It would lead to something like a yes-no response. It would lead to determining success or failure. It would lead to maybe agreeing or disagreeing. So, for example, in the M&Ms example that I shared with you, I would basically look at each M&M and decide, is this orange or no? Yes or no? And in the end, I'd count the number of yeses and I'd determine the proportion that are orange. I might think of success as being I've grabbed an M&M and it's orange, and a failure would be that it's not orange. So again, think about how the data was originally collected. Each individual case, was that giving you an amount of something, or is that giving you a category? Is that giving you a yes-no type response? And in the examples we'll go through, we'll always ask this question, just so we kind of know right from the start what kind of data are we dealing with. It's important, again, to know some symbols here that relate to proportions, and I've already talked through a lot of these, but I wanted to have this slide here for you to refer to later. So make sure you understand that if you have a sample proportion, it's a P, and it has this little symbol on top. We call this a hat, so H-A-T. So sometimes we might say P hat, and that means the sample proportion. P is the population proportion, and N is our sample size. to find a sample proportion. So you might be given a scenario and we don't actually tell you the sample proportion, but we give you the information that you can figure that out. So you take the count of successes in the sample divided by the total sample size. So if we go back to our M&M example, for instance, let's say I tell you that we have 15 total M&Ms and 5 of them are orange. And again, orange is being successful because we want to see how many oranges we have. If it's orange, it's a success. So you could take 5 and divide by 15, and then you would find your actual sample proportion. Okay, so let's jump into an example we'll work with a little bit in these slides. Here's a big, huge bag of beans. And hopefully you can see here that we have several white beans. We also have several red beans, lots and lots of beans. And we're going to consider this huge bag of beans a population. And what we want to do is we want to estimate the proportion of red beans in the population. So that's what we're going to do here. So in this case, success would be getting a red bean. So we're imagining we're going to take a sample and we're going to look at each of the beans, and if it's red, we say yes, we have success, we have a red. If it's orange or if it's white, we would say no, we have no success, there's failure. So we're going to count the number of successes, the number of red beans in our sample. So again, I want to figure out the proportion of red beans, but I'm lazy. I do not want to dump out this huge bag of beans. I think I'm going to make a mess. I might lose some beans in the process. My cats are going to get into all these beans and they're going to be all over the house. So for whatever reason, we're not able to actually count all the beans. And even if we could take a census, it's possible we could make errors in counting because there are so many beans, it would be very tedious. So lucky for us, we don't have to do that. We can take a random sample from the population. We can count the number of successes, the number of red beans. We can determine the proportion of red beans we get in our sample, and we can use that information to actually estimate what's going on in the population. So let's look at what this would look like. So I decided I'm going to take a sample of 25. So n equals 25. Here's my sample. I took a picture for you. And I see that 4 out of my 25 beans are red. And if I actually take 4 divided by 25, that's going to give me p hat, my sample proportion, and it's going to equal 0.16. So ideally, in this particular chapter, we want you to keep these proportions in the form of decimals. Certainly though, we could, if we wanted to, we could report that as a percentage. So 0.16 times 100% would give us 16%. So we could talk about this in terms of percentage or proportions. So I've taken the sample of size 25. Does this mean that, and I find that I have 4 red beans, does this mean that 16% of the population must be red? So hopefully you're thinking not necessarily, and hopefully you're thinking again of sampling variability, that this is just one sample. We would need to know what we would see with other samples. Well, let's take a look. I took another sample just to kind of check and see what was going on, and here I found that 9 of 25 beans are red. So I'm getting a different proportion. I have more now that are red. Again, why is this different from the first? Did we make a mistake? Hopefully you're thinking about the fact that just by chance we're going to get different things. Each time we sample, we're going to get a different collection of beans and we're going to have different results. So this is expected. We didn't necessarily make a mistake. We expect to see differences from sample to sample. One more here. Now I get 8 out of 25. So the big question, how do we really know what's going on in the population if every single time we sample we get something different? So I'm going to pause here. I want you to think about that, and then we're going to come right back and talk about what's going on.